Thank you for the introduction, and thank you for having me here to give a talk. So I'll start by saying my talk is not that deeply related to free probability at all. This talk is more about approximations of groups by permutation, which is something of concern to free probability, but not really going to talk too much about connections to free probability or anything of the sort, because admittedly I'm not an expert in free probability. I'm still learning that. So I guess this is the last talk of the day, so you guys might already be tired, so it's probably a good thing that I'm not talking about anything that important to a large amount of the audience here. So of course, if I'm talking about Sofic actions on sets and graphs, I should define what soficity means. This is something introduced in the 90s. So the idea is we want to understand. So when are groups capable of being approximated by some finitary objects? So the purpose of studying probability, you might be wondering, if you are capable of being approximated by finitary objects, then you can consider maybe measures on matrix algebra or stuff like that. You can define entropy and stuff. In general, it's just impossible to do these kind of things without finitary approximation. So for groups, we're specifically concerned about approximating group relations. It's using permutation groups. There are different ways of doing this, but if you require, say, we're actually approximating by a permutation group up to eventually a relation should hold in permutation group, that's generally speaking too strong a condition to require. Instead, we're sort of saying eventually I want every group relation to hold approximately in the permutation group with respect to some reasonable definition of distance, which for Sofic groups we use this normalized Hamming distance. So I'll write down the definition here. Group G is called Sofic if there exists a sequence of map into some larger and larger finitary permutation groups such that phi n, such that for all g and h in the group, phi n of gh minus, well, I shouldn't say minus, phi n of h, the normalized Hamming distance of this goes to 0, and for all g in the group, which is not the identity element, I want this thing to be far away from 1. Sure. So that's the next thing I'm about to do. So the normalized Hamming distance really, the usual Hamming distance really is just counting how many things you moved. So if you have an element of the permutation group, the Hamming distance between G and H is really the number of the, this is elements of the symmetric group on n elements. K in the set of n elements such that G applied to K is not equals to H applied to K. So really, how many elements are they different between the two groups?
Bottom line, your limit should go to 1.
Wait.
Bottom line.
Oh, this one?
Yeah.
Oh, sure. Yeah.
You want to divide by n.
Yeah, no, that's why I write D here. Yeah, I read a different distance. So this is the usual Hamming distance. The issue here is that this distance would at least be 1, and you want some more, you want things to approximate to 0, and if it's at least as 1, that's not really helpful, so you divide this by n. So this basically is more probabilistic, essentially.
That's really the Hamming distance of the vector, right?
Sure, yeah.
The permutation.
I guess you can also regard this as if you uniformly randomly chose element in n, what's the probability of them being sent to different things, basically. So you can use that to generalize Hamming distance to arbitrary probability space if you want. So So it's actually a well-known open question in group theory whether all groups are Sofic. This would imply all groups are, for those of you familiar with operator algebras in the audience, all groups being Sofic would in particular implies all group phonema algebras are constant-embeddable, because basically you can embed symmetric groups into unitary groups of n-by-n matrices. It's also known that soficity is preserved by various usual constructions in group theory. So, for example, like if G1, if Gi are Sofic, that implies G1 Gn is Sofic. It's also true that if you take G1 star H G2, the amalgamated free products, this is Sofic. If Gi Sofic and H amenable. You can also do this with HN extensions or amenable groups. You can also extend by an amenable group. You can also do graph products. You can also, this is a result by Mejias and Andrew Sale in 2018. You can also do this for wreath products. So, yeah.
All finite groups, Sofic.
Yes, finite groups are in particular Sofic. Amenable groups are all Sofic. By basically cutting down to the former sets.
Okay.
Can you comment on the significance of this normalized Hamming metric? I mean, we could replace the Hamming metric here by anything else, right? Like the infinity metric or some other, like L2 metric. We get a different notion, presumably.
Sure.
Right?
2 metric wouldn't change. The only thing that would change is infinity metric. Or at least if I'm regarding these as like operators, if you regard these by matrices, you can replace the Hamming distance by normalize LP distance for any p smaller than infinity, larger than or equal to 1. They all give you the exact same notion because on unitary group they're all equivalent, the distances. If you change this to infinity, then this is a completely different notion. This is this is a slightly different topic in group theory. Like there, for example, you might want to study like different kinds of stability with respect to like different kinds of notions approximations. I believe they yield very different class of groups that are stable. I don't exactly remember which are. And also, if you like don't normalize this, this is trivial, right? This just forces us to equal at some point, so that really just tell you the group is, I think group theory is called this finally presentable or something. And if you are finally generated group, this literally just a finally presented group that literally just means it's like a residue finite. So
there's some notion that this is just the right metric to get a non-trivial notion of finite approximate. Or is the definition motivated by the fact that there are certain things that are continuous with respect to these metrics?
Yeah. I guess it's just if you're looking this into operator algebra perspective, this is a natural metric because this corresponds to basically the normalized 2 norm. So this is basically saying you're embedded into matrix algebra product such that all the sequences are actually permutation matrices. So that will correspond to precisely this normalized Hamming distance. And again, you could change the normalized Hamming distance to LP distance for any P as long as it's not infinity. Okay, so there's another result proved by Sri, me, and Mahan, where we proved that you can also do this for group doubles of Sofic groups over separable subgroups. But it doesn't really matter for the purpose here. I'm just saying like you can prove a large amount of groups that are actually like large amount of operations preserve soficity for groups. So some particular open questions are like here is saying like soficity is preserved by amalgamated fructose if the amalgam is amenable. It's not known if this is true if amalgam is just arbitrary subgroup. It's also not known whether, as I said, like soficity is preserved by extension by amenable groups. So same question can be asked whether it's stable under extension by Sofic groups. That's also not known. And as I mentioned, a result of Ben-Hayes and Joussel proved that this soficity is preserved by wreath products. So it's a question whether you can consider generalized wreath product, whether that's still preserving soficity. One of the main reason this study of Sofic actions on sets and graphs, which I forgot to mention, is joint work with Gregory, Patchell, and Sri. So I should mention that before. I apologize for that. One of the main reason we started this research is to generalize this result on wreath product to consider a more general class of actions of a Sofic group or more general groups on sets, and ask whether that ends up giving you soficity of the generalized wreath products. So that's one of the motivation. The other motivation is that there are already notions of Sofic actions. It's just they're not discrete actions like what we did on sets and on graphs, but rather there are notions of Sofic PMP actions. So if you have a group acting on probability space, there is a natural notion of Sofic action, which is easier to explain in operator algebra language. The idea is basically you can have an L infinity of the operator space, the probability space, omega, whatever. And you have your group acting on this space in a probability preserving way. So this is the group from the group measure space from the algebra. And this thing embeds into the matrix ultra product in a trace preserving way, so that the L infinity here sends to a natural corresponding L infinity here, namely to the diagonal matrices, and G are sent to permutation matrices. Yeah.
Another really basic question based on what's on the board there. Are all of the common matrix groups Sofic? So for example, the general linear group or the unitary group?
Usually we're considering those in the context of discrete groups, so it would be a different matter to discuss it for locally compact groups.
Okay.
So.
As discrete groups, any linear.
Sorry?
As discrete groups, any linear group.
They're Sofic because it's residue finite. Yeah. Yes, because general linear group is residue finite, so all matrix group are residue finite, so if you consider them as discrete group, they're Sofic. Because in particular, you can just choose finite quotients and send G to symmetric groups on basically the finite quotients. Okay, so this is a great notion of actions on a probability space, but doesn't really help you if you're talking about actions of a group on a set or actions of a group on, we'll talk about later, of graphs, which is actually a generalization of our notions of Sofic actions on sets. So the thing here is usually when you talk about soficity, you want to identify these things that are essentially finite sets. So in here, I'm saying the group acting on the finite sets of elements D, and there's some notion of approximation there, such that this action basically approximately give you the group structure. Here you can see similarly, you can consider this L infinity, the probability space being acted on is being approximated by, again, this is, you can treat this as if it's basically an element set with the uniform measure. And the group, again, are being acted on this set of n elements. So, and that's approximate your action and your group in an appropriate way. So if we're talking about actions on sets and actions on sets, we would need something similar to this. So here is the notion we end up coming to. So I'll write the ultra product version because it's just happens to be easier. So usually you might want to consider acting on n-element sets because that's the usual thing that would happen. But it turns out that's more suitable for talking about probability measure preserving action rather than action on discrete sets. So instead, what you do, you consider acting on the set of all functions from n-element sets to some universal set. I'm just using natural numbers here. Any infinite set would work. And you can equip this with normalized Hamming distance again. And this is a metric space. So you can take what is known as metric space ultra product. So what this means is that you are considering sequence of points in these metric spaces, and you're identifying two sequences if you know the distance between the two sequence of points converge to 0 under the ultra filter. So this turns out to be sort of a natural kind of universal finitary projects for finitary objects for sets. And there's a natural action of the ultra-productive permutation groups. Again, this is normalized Hamming distance. I'm identifying two sequences of permutations to be the same if under normalized Hamming distance, their distance goes to 0. This thing naturally acts on here because as n, the permutation group on n elements naturally acts on the set of n elements. So I just induce action on the sets of functions. Yes?
I mean, is this the same as just changing your C over here to n in this previous attempt?
This one?
Yeah.
Sure, yes. I mean, sure, but like, I guess the issue here is that when you're doing here for C, you're taking quotient with 2 norm going to 0. This is not exactly the same, but yeah. And this is basically the universal finitary objects we're trying to identify for Sofic actions on sets. So really Sofic action of G on some set X. Being Sofic, I'm just defining this to mean there is a group homomorphism here, and there is an isometric embedding here. And by isometric, I mean I'm equipping my set with the discrete metric. And such that this diagram commute in the sense that if I ax here and go through this isometric embedding, I get the same thing as if I go through the isometric embedding and I go through the group homomorphism and ax here. So the same thing works if you do this for graphs instead of doing n to the set of functions from to n. You change this n to some universal countable graph, say disjoint union of all finite graphs. By universal, I just mean all finite graphs embedded into it. So you can change this to disjoint union of all finite graphs or any other countable universal graph, which in particular includes like almost surely every random graph on n would satisfy this condition. So, and then you have a similar version of this where you include this to be isometric and also preserves the graph structure in some way. You can write down finitary versions of this. I'm not going to because it's just technical and doesn't really that sound that much interesting if you just look at it from a finitary perspective. So one of the things here is that I specifically require this to only be a group homomorphism, but you can also ask this to be injective group homomorphism. The reason I did it this way is just because it's slightly easier to stay this way, and that means you can have non-Sofic groups acting Sofically on set. But if you want to exclude that case, you could just require this to be injective. Okay. So, I don't have that much time, so I'll just basically collect all the interesting results here. If G acts on X is Sofic, G is Sofic itself, H is Sofic, then the generalized wreath product is Sofic. The generalized wreath product is just H direct sum X, and G acts on this by permuting the direct summons. Similarly, you can do this for graph. If you have G acts on some graph is Sofic. I shouldn't use G for gamma here, maybe. Sofic, G is Sofic, H is Sofic. Then you can do this, what we call the graph wreath product is Sofic. Here, the graph wreath product really just means you take the graph products with respect to gamma, and all vertices set to H, and then G acts on the graph products by, again, permuting the vertices. Yes?
So does your first result recover this result you mentioned of bends?
Yes, so that's
what's X and what's alpha in that case?
Yes, that's the next thing I'm about to say is that for any group, you have the natural left regular action on itself, and that's Sofic if and only if the group is Sofic. So left multiplication, this is Sofic, if and only if G is Sofic. So in particular, this recovers Ben and Andrew's result on the wreath product being Sofic.
So why does the lack of assumed injectivity of phi not get in the way then here?
So the thing here is I'm doing this in a way so that essentially what ends up being Sofic is like a quotient of G acting on it. Basically, you consider the quotient of G by the kernel, and that thing acts on, that thing still acts on X, and that's basically what's the thing that's actually Sofic. So, and that means just assuming G is Sofic to start with, so you can just assume it's injective if you want. The reason I wrote it that way is because you can also apply Sofic actions to groups that are not Sofic. And that's
Right, I guess I'm interested in the left to right direction.
Oh, you mean here?
Yeah, because it seems like, I guess if it's not an intuitive thing, you can just...
Because this thing is isometric. So in particular, this G is injective into here, and that basically enforces this to be injective. So, in fact, you can just say that, in fact, it's just generally the case that if G acts on X is Sofic, then there is a normal subgroup containing G, and N is a subgroup of the kernel of this action such that G divided by N is Sofic. This N is really the kernel of phi here. So, in particular, if you have a faithful action, this kernel is trivial, so N is trivial, so that tells you G is Sofic. Okay. I should also mention the graph result recovers the set result because you can just consider a group acting on a set, but then pretend the set is a graph by just like including no edges. Or, I guess if you're trying to do this, you should include all edges. So consider the complete graph on X. And then G acts on the complete graph is Sofic, and prove that if and only if G acts on the set is Sofic. And if you consider the complete graph, then the graph product is actually just a direct sum. So the graph wreath product is actually just a usual generalized wreath product. So, so you can also do this. The reason I didn't require G to be Sofic in Sofic action is that you can also apply this to cases where G, you're not assuming G is Sofic. That could still give you interesting results. For example, you can replace G being Sofic to G being hyperlinear. For those of you who are operator algebras, it just means the group phoneme algebra is const-embeddable. If you want more direct versions, it just means you can do the same thing as soficity, but instead of going to symmetric group, you go into unitary group of embedded matrices, and instead of normalized Hamming distance, you take normalized L2 distance. G is Sofic. Instead of saying H is Sofic, I take a constant-embedable phoneme algebra. Constant-embedable. And then you can do the similar construction here to take a phoneme algebra, generalized wreath product, and this is constant-embedable. So this one does not require you to assume G is Sofic. And similarly for here, you can do the exact same changes. So this is the first interesting example of Sofic action. So now let me generalize this by saying that not just G acts on itself being Sofic, but actually G acts on any set with a amenable stabilizer is actually Sofic if G is Sofic. So not just G acts on itself at left regular representation, you can actually let G acts on the left cosets of G over some amenable subgroup. It still works. You can also do this for graphs, where we prove that G acts on any graph in a transitive way, again with amenable stabilizer. Those actions are Sofic. We cannot remove the transitive assumption in graphs for some reason, because for sets, really, because like you can restrict to each of the orbits and they're all Sofic, then everything's fine. For graphs, there's an issue of like different orbits, how they're connected, edge connected to each other. So we cannot remove the assumption of the action being transitive. Some other important examples of Sofic actions include any action of a amenable group is Sofic. Again, this is just using Foner sets. Another perhaps surprising example is any action of free groups is actually Sofic. So one of the reasons here is essentially because there are lots of group homomorphisms from free groups. So it's very easy to achieve this side here. And then for this side, you're essentially just including a large enough subset of the original set, and then you're basically done. So I'm not going to write down the proof, but the idea is basically once you have a sufficient amount of group homomorphism, then it's easy to ensure that it has Sofic actions. So yeah, let's give you another proof of free groups being Sofic, but I guess that's a bit of a boring proof. This actually also works for not just for sets, but also for graphs, where the proof is slightly more complicated because it involves you having to prove some kind of extension properties for graphs, which is apparently already known in to graph series. So, some other thing including here is that you can do limits of Sofic action, and they're still Sofic. So here you need some very reasonable definition of what limits means. But let's just consider the set case and give you a particular example. So if you have a sequence of subgroup of G, and let's say this converges to a subgroup H, this is a Srivatsav topology, which really just means the indicator function converges to indicator function pointwise. So this is, and let's suppose G acts on G divided by Hn. Let's suppose these are all Sofic. Then this in particular implies G acts on G over H is also Sofic. You have a similar version for graphs where you have to be more sophisticated as to how you define this notion of convergence, but you can. It's not really that hard to write down a definition. For groups, this is what for like acting on sets, this is basically what amounts to. And this does have one very interesting application, namely, it implies all actions of what is known as LERF groups are Sofic. So all actions of LERF groups are Sofic. This is locally extended residually finite. It means for any finitely generated subgroup, this is separable in G. And by separable, I mean there exists Hn decreasing such that the intersection of Hn is H. And furthermore, these are all finite index. In case H is a normal subgroup, this is equivalent to saying G mod H is residue finite.
This is true for all finitely generated subgroups?
No, this is a special property for, I'm saying G is LERF. Oh, you mean like if for specific G?
I'm asking what's the quantifier on H?
Okay. Yeah. Okay. So you mean whether all groups are LERF? That's definitely not true. Okay. So a classical example of LERF group is all free groups. They're all LERF. So you can use this to prove. You can use this limiting procedure to prove all. You can use this limiting procedure to prove all actions of Sofic, of LERF groups are Sofic. So the way you do this is noting that if this is this Hn here is this decreasing sequence, then you're acting on a finite set. It's not really hard to prove that any action of a group on a finite set is always Sofic. So these are always Sofic that tell you G acts on G over H for any finitely generated H is Sofic. But then if you have an infinitely generated subgroup H, you can just take an increasing sequence of finitely generated subgroup. And again, that also do pointwise convergence, so you also get this for infinitely generated subgroup of stabilizers. So yeah, in particular, this also recovers the result that all free groups are Sofic, but it also tells you, say, all actions of Sofic groups were Sofic and stuff like that.
Was it previously known that all LERF groups were Sofic?
Yes, LERF groups in particular implies it's residue finite because you can choose H to be the trivial subgroup, right? So yeah, the interesting here is telling you that you can take any LERF group, you can access on any way on a set, and the generalized wreath product is still Sofic. That's the main interesting thing here. I think that's basically my time. Or do I still have a few minutes?
You have until 50 minutes. You have another 5 minutes.
Okay. I guess I'll just write down the version of this for graphs and then end it there. So you have a similar notion for limits of graph actions. So in which you have to first choose G, a group, acts on some graph gamma n, where some action alpha n, and you have to choose a distinguished vertex Vn in the graph, which really corresponds to Hn in this G mod Hn. And I say this converges to here if for all finite subset of G for large n, or I guess just there exists n such that whenever m, there exists n such that whenever n larger than equal to n, alpha n G Vn equals Vn if and only if alpha G V equals V for all G and alpha n G Vn is connected to Vn if and only if alpha G V is connected to V for all G and F. So the first one really is just, this one really just corresponds to the stabilizer converging. And this one is sort of telling you that it also preserves the edge relation. And if all these alpha n are Sofic, then this implies alpha is Sofic. Finally, let me mention a few open questions. So one of the main open question here is whether if you consider G acts, if you consider two commuting actions, in fact, you can just consider this in the set context. So if you have G acts on X and H also acts on X, and assume the two actions commute, then you naturally have an action of G cross H on X. So whether these two being Sofic imply this is Sofic. This is a particularly interesting question because this will imply generalized wreath product being Sofic implies implies the action is Sofic. And the reason basically being the action alpha here is basically encoded in the conjugation action of G on the larger group. And the conjugation action is the direct sum of two permuting actions, namely the left multiplication and the right multiplication. So similarly, you could also ask whether G star H acting on X is Sofic. Whenever, in this case, you don't require the two actions being commuting. And again, we don't know whether this is true or not. OK, I think that's all I want to say. Thank you.